Okay, so uh, in the previous lecture, we have talked about we have started the chapter isomorphisms. So we have given some motivation about that, how we can identify one group by another, or like we can show a map which is an isomorphism between two groups. We have explained that many things. We have also explained that there are 4 steps to show an isomorphism. You have to first show that there's a mapping, then you need to show that the mapping is 1-to-1, then you need to show that the mapping is onto, and then you need to show that the mapping preserve the operation. Similarly, we have given a bunch of examples. Now, I also want to give one more example, and then we will do some important theorems related to the isomorphism. So, example 6, we call it. So, we have a group G, which is SL2R, which is SL2R. Just give me a second. SL2R. This is the group of 2 cross 2 real matrices with determinant 1. And let M be any M 2 cross 2 real matrix with a determinant 1. So let's say M belongs to SL2 SL2R, right? Then we can define a mapping from G to G itself. Then we define a mapping phi from G to G itself by phi of M as A M A M inverse for all A in G. And to verify that phi is an isomorphism, we carry out the 4 steps. Right? So step 1 is that phi is a function from G to G. Phi M is a function from G to G. Here, we must show that phi M of A is indeed an element of G whenever A is, right? This follows from the properties of the determinants. So you can say that determinant of M A M inverse is nothing but the determinant of M, determinant of A, and the determinant of M inverse, or the determinant M inverse. And as we know, M is an element of SL2R. It has determinant 1, so it is 1 dot 1 inverse, and all the elements in G should have determinant 1 also, because G is SL2R. So everything is equal to 1. So the determinant of MAM inverse is also 1. Thus, MAM inverse is in G. Perfect. So whatever the element we take from G, if we apply phi M over it, it is still inside G. So phi M is a well-defined map. Perfect one. Perfect. Number 2. Now, step 2 says we need to show that phi m is 1, 1. 1, 2, 1. To do that, suppose that phi m of A is equal to phi m of B. Then m A inverse is m B inverse, and by left and right cancellation, A is equal to B. So this shows phi is 1 to 1. Phi m is 1 to 1. Step 3, we need to show that phi m is onto. For that we say that let B is an element of G. We must find a matrix A and G such that phi m of A is B. Now, how shall we do this? Such a matrix A is to exist. It must have the property that this must have the property that m A m inverse is B. But this tells us exactly what A must be. So for we can solve for A to obtain. So solve for A, we obtain A is equals to m inverse Bm, and verify that phi m of A is m A m inverse, which is m inverse Bm. M inverse is nothing but B. Perfect. Number 4 is operation preserving. So I need to show phi is operation preserving. So phi m is operation preserving. Let A and B, A comma B, belong to G, then I can just write phi m of A B is equal to m A B m inverse, that is m A m inverse m B m inverse, and we can just expand that as m A m inverse and m be M inverse, and that is nothing but phi M of A and phi M of B. Perfect. Now the mapping phi M is called conjugation phi M. So it's indeed an isomorphism. Now we will talk about some important theorems related to isomorphisms, and that will actually blow mind because they blowed the minds of many mathematicians when they were firstly discovered. So let's talk about Cayley theorem. Cayley's theorem. Perfect. This is our first theorem is the classical result of Cayley. An important generalization of it will be given in chapter number 25, which we will hope learn. But at this time, we have theorem 6.1. We call it Cayley's theorem. From 1854. The statement is every group is isomorphic to a group of permutations. And how fascinating that statement is. So every group you can imagine in the entire world is isomorphic to some group of permutations. There exists a group, for any group, there exists a permutation group, and they both are isomorphic to each other. And for this, to prove this, we will first define a certain way of writing a permutation group, and then we will call, and we can extend this notion and generalize and say that every group can be, so like for every group, a permutation group can be obtained by that way. Okay, so proof. Proof is quite simple, not that hard. We can do that. So let's say G be any group. Date G be any group. We must find a group. We must find a group G bar of permutations that we believe is isomorphic to G. Right? Now, since G is all we have to work with, we will have to use it to construct G bar. So we will use G to construct G bar, construct G bar, G bar. which is a group of permutations. So for any element G in the group G, we define a function is Tg from G to G by Tg of x is equal to G into x for all the elements x in G. Okay, so the small g, the element G is also an element of the group G, and this x is also an element of the group X. Okay, you can say in words, Tg is just the multiplication by G on the left. By G on the left. Perfect. Now, you can indeed think Tg is a permutation on the set of elements of G, because Tg is a permutation on the elements of G, because you can think of it as, imagine you are multiplying two elements of the group or having an operation between them. They will always give you a third element of the group, or the one of them. Now, by doing that, you are actually going from those two elements to either one of them or the third one. And that is actually a permutation, like moving from one place to the other place in the sense of places. So you can prove that Tg is indeed a permutation of the group. Now, let G bar is a group which has all these Tg's, given that G element G is in the group G. So we have generated the group G bar by these functions Tg. So all these functions Tg's are an element, are the elements inside the group G bar. Okay, perfect. Now, and this is a group under the function composition. You can say then G bar is a group under function composition. Okay, perfect. Now to verify this, we need to show all these four steps. All these four steps of the isomorphism. So let's start the first one. So let's write that. We first observe that we first observe that for any element G and element H in the group G, we have dg into dh of x is equal to dg applied dh on x, and that is nothing but dg hx, and that is nothing but g into hx, and that can be written as GHX. And finally, okay, if I just write that on next line, or I can just say finally, that will be equal to TGHX, right? So that, so that we can say TG into TH is nothing but TGH, right? From this, it follows that from this, it follows that TE is the identity, and TG of inverse, TG inverse is nothing but TG inverse, right? Since function composition is associative, we have verified all the conditions for G bar to be a group, okay? Perfect. Now the isomorphism phi from G to G bar is ready-made. So for every, because for every element G in group G, we define phi of G as TG. Perfect. Now, if TG is TH, TG is TH, then TG of E is equal to TH of E, or we can say GE is equal to HE. Thus, we can say G is H, and that give us 1 to 1, and phi is 1 to 1. By the way, G bar was constructed. We see that phi is onto is G bar was constructed. We see that phi is onto okay. The only condition that remains to be checked is that phi is operation preserving. So to this end, let A and B belong to G, then phi of AB is equal to TA, TB, or even phi of AB is equal to TAB, which can also be written as TATB, and that's nothing but phi of A, phi of yeah. So the group G bar constructed previously, okay, and then the group G bar constructed previously is called the left regular representation of G, which is you don't have to worry about this at this time. You'll you'll learn that if you take a course in the group representation theory. Perfect. So example 7 will present now. Example 7 says, for concreteness, let us calculate the left regular representation U bar, U12, U of 12 bar for U of 12. So compute U of 12 bar for U of 12, which is 1, 5, 7, 11. Now, writing the permutations of U of 12 in array form, we have so let's say we have the permutation T1, which is 1, 1, 5, 5, 7, 7, 11, 11. We have the permutation T5, 1, 5, 5, 1, 7, 11, 11, 7. Remember, Tx was just the multiplication by x. Tx is just a multiplication by x. Okay. Okay. And then we have T7, which is 1 to 7, 5 to 11, 7 to 1, 11 to 5. How are these elements are changing? Because you are multiplying 7 to 1 and then 7 to 5, which is 35. And then you are doing modulo 12, 35 modulo 12. Okay, so that would be either 24 and then subtract 35, that is 11. So that's how you get 11 there. And then 7, which is 49. So 49 modulo 12 is 1. And then 77 modulo 12 is 5. That's how we are getting all these different elements in the second row. Because Tx is just the multiplication by x. Okay, perfect. Now these are the permutations of U12, U of 12 in array form. Okay, now what can we do? Let's compare the Cayley tables. Compare the Cayley tables for U12 and U of 12 bar, right? So let's say we have U12, We have 1, 5, 7, 11. We also have 1, 5, 7, 11. What can we do? 1, 5, 7, 11, 5, 7, 11. Then we have 1, 11, 7. And we have 1, 5, sorry, 11, 1, 5, and we have 7, 5, 1. Okay, this is U12. You want to write U12 bar. We have T1, T5, T7, T11, T1, T5, T7, T11. Right? So the first one will be same. Over here also. Okay. And everything would be similar to the table of U12. So you have T1, T11, T7, and then we have T11, T1, T5, and we have T7, T5, and T1. That's it. These are the tables. U12 and U bar. Perfect. Okay, that's it. We will talk about properties of isomorphisms in the next two results. Thank you.